good afternoon, everyone. I think we've got everybody mostly back in the room. It's my pleasure to be the kind of chair of this afternoon session. We have a total of 4 talks with a coffee break in the middle. And I've been reassured by Jane we will have coffee to sustain us. And there's also a nice structure to this afternoon session. We'll hear this morning from Åsa Larson and also Xavier Urban. And they'll be talking about the role of these long-range ion pair states in scattering applications. Åsa will talk to us about the theory, and Xavier a little bit about the experiments. So why don't I turn it over to Åsa Larson right now. She'll be telling us about reactive collisions involving ion pair states.
Thank you. Do you hear me? So it's an honor for me to be here. Before I came here, I didn't know much about heavy Rydberg states, so I'm here for learning. But what I'm doing is kind of related, as you will see. So I will start with an introduction, describing the processes I'm studying, and giving some examples of experiments that are carried out relevant for these. And then I will go through different examples, different systems, H plus and H minus, H2 plus plus H minus, H plus plus F minus, helium plus and H minus. And I will end with a summary. So the processes I'm studying have in common that you either start or you finish on the ion pair state. In ion pair recombination, you can have different reactions occurring. You can have a charge transfer, mutual neutralization, where neutral atoms are formed, or both electrons can be transferred and you have double charge transfer. Or the molecular system formed can auto-ionize and you have associative ionization or electron detachment. We have also ion pair formation. For example, you can form an ion pair by absorbing photons. Or you can recombine a molecular ion with an electron. The molecular system formed can dissociate into the ion pair fragments. So electron recombination, or you can have the opposite of mutual neutralization. So what I'm focusing on here are the processes mutual neutralization, double charge transfer, and ion pair formation in electron recombination. So I'm doing theoretical studies, and my studies are motivated by experiments. And for a very long time, I studied dissociative recombination. And these types of processes have been studied in, for example, cryo-ring that was situated in Stockholm, where molecular ions were stored in this ring and merged with electrons here. And you studied low energy collisions between molecular ions and electrons. And then by detecting the fragments, you could detect, for example, the ion pair formed in the processes. This ring is now mounted down. It's shipped, or it will be shipped to Germany. Instead, they are building a new storage device in Stockholm. And this device, Desiree, is an electrostatic storage device. Here they will store positive ions and negative ions. And in one section here, they are merged, the two beams. And you can study, for example, mutual neutralization. So this is now, it's under construction, and they have gone quite far now. They are pumping down this thing. It will be cooled down to like 10 Kelvin or something like that. And the goal is to have the first experiment before the end of the year. Okay, so some theoretical considerations. And as an example, I show you now the potentials of H2. These are the singlet sigma Gerade plus potential curves, the adiabatic potentials that you have seen earlier this morning. Here you see the ground state is not shown in this figure, and you see the potential curves, and you see this ion pair state interacting with the Rydberg states. The dashed curve here is the ion potential. And as you all know, the ion pair curve can be described by this long range, this ion potential, and that's shown with the red curve now. So this is kind of a quasi-diabatic potential of the ion pair state. If we zoom in at small distances, you see you have avoided crossings also here. And typically when we do studies of dissociative recombination, what you do is you diabatize this resonant state here. That's a 2p sigma u squared resonant state. You diabatize this potential relative to the Rydberg manifold here. And the potentials that I'm showing here are what I will call quasi-diabatic potentials. You have electronic couplings between them, but you also have remaining non-adiabatic couplings that you have to consider. These are kind of quasi-diabatic potentials now if you go from, I show them here both at small distances and at larger distances. An alternative approach, instead of using these quasi-diabatic potentials, is to do a strict diabatization procedure where you say that you only include a finite number of states. You calculate the non-adiabatic couplings among these, and you form diabatic states where the non-adiabatic couplings are 0. And you do that by solving this equation here, where this matrix here is a non-adiabatic coupling, and T is a transformation matrix between the adiabatic and diabatic states. And then you get the diabatic potentials by just transforming the adiabatic potentials. This is an alternative approach, and if you looked at these potentials, they don't look at all as the quasi-diabatic potentials I showed you before. Okay, so to describe the processes, we have to deal with a long-range Coulomb potential. We are dealing with highly excited states, you all know that. And we have to include these non-adiabatic couplings. And some of the couplings are occurring at very large distances. And if you do quantum chemistry, you know that that's not easy to calculate. Furthermore, you saw that you have couplings here also to the ionization continuum. And you have to link the bound state calculations with electron scattering calculations. And usually we do some kind of diabatization procedure, either using quasi-diabatic potentials or a strict diabatization. But the problem is that we are, as you all know, we are dealing with, in principle, an infinite number of interacting states. We have to include, in many cases, high angular momentum. And what we want to do is a quantum mechanical study, an ab initio study. So let me show you some examples, H plus plus H minus. We start with that one. And I will show you results from our study on mutual neutralization on H plus plus H minus. So H plus plus H minus, an electron is transferred, and you form H in some excited state plus H in the ground state. Here you have the reference. So what we did in this study is the goal was to calculate the low energy cross-section. Low energy is below 100 electron volt. And we wanted to do it quantum mechanically, include the electronic vibration and rotational motions quantum mechanically. We started by doing structure calculations using full configuration interaction method quite a large basis set. And that's because we wanted to have the grad and ungrad potentials and the non-adiabatic couplings at all distances from the same calculation. Of course, in the literature, there are very good calculations that we could compare with. Here we included states up to the n equals 3 limit plus the ion pair state. So that means for the Grad symmetry, we included 7 states. For the ungrad symmetry, 6 states. And we did the strict diabatization procedure I mentioned before. So we didn't include, for example, we didn't include the coupling to the ionization continuum. We included the fact that the nuclei are identical, and we used, instead of solving the coupled radial Schrödinger equation, we solved the a matrix Riccati equation for the logarithmic derivative of the radial wave functions. This is the result. And now I actually compare her here with the results by Xavier that I hope you will talk more about in the next talk. So the first experiment, and actually until Xavier did this, the only experiment at low energy was this by Moseley. There has been a number of experiments at higher energies where you see the cross-section goes up again. Our result is a black curve, and you see at low energy it falls off as 1 OE, and then it goes up again. So this is a total cross-section that we calculated. We also could see what fragments are formed, and here we compare with the results by Xavier again, the branching ratios, and you can see that at low energy, everything goes to n equals 3, and then at higher energy, when the cross-section started to go up again, you see a switch in the branching ratio. This is some new results. I actually got it yesterday. So when we do this, in principle, we obtain the S matrix. And from that, we can get information about not only the total cross-section, but also the differential cross-section. And this is what it looks like, what I got just before I left, for some energies here. Then we have also studied double charge transfer, where both electrons are transferred. We did it both for H plus H minus and also D plus H minus. D plus H minus might be easier if you do an experiment. And this is the result. You see it goes like 1 OE, and then you see some oscillations here. The difference in oscillations can be more or less explained by just the difference in reduced mass between the systems. This is how it looks compared with other theoretical and experimental measurements. So you see most of them are at higher energies. Our result is the black one here. And you see it merges into several of these theoretical studies, but there is a factor of 10 difference still between our result and the experiments. And this we don't yet understand. Okay, I also mentioned ion pair formation. And here, instead of coming in on the ion pair, we go out. So here we study electron recombination with HD plus, forming this ion pair. The reason why we take HD is that because in the experiment, if you have HD plus, it will relax vibrationally. So you know what vibrational state you start with. The measured cross-section that they measured at Cry-ring showed oscillations as a function of energy. And when we do this, we use these quasi-diabatic potentials that I showed you before. And the oscillations can be understood by just quantum interference between different pathways here. So either you capture an electron from the ion, you go to this resonant state, the red one here, you follow it diabatically all the way to the ion pair, or you make transitions to one of the Rydbergs. And then these different paths will interfere. This is the result from our study here. the experiment is black, theory is red, and as you can see, they are similar, not perfect agreement. The higher energy here, I mean, here we know that higher excited state that we didn't include in the calculation becomes important. It should be also noted that in this study, and in many of these studies, we only included the electronic couplings among the states. We didn't include any non-adiabatic couplings, even though these are not strictly diabatic states. H2 plus H minus. Okay, here we have studied ion pair formation. Again, H3 plus now recombines with electron, forming H2 plus H minus. And if you look at the potentials now, the quasi-diabatic potentials, here you see the system, and we're using these Jacobi coordinates, where in this figure, R is frozen to the equilibrium distance of H3 plus. If you look at the potentials here, the ion is a dashed one. You see they look kind of similar to the H2 plus, H2 potentials. You have resonant states. Here you have two resonant states, and they are crossing the Rydberg states both at small and larger distances. First, we just did a 1D calculation, freezing both the R and the theta. And this is the result from that study. These are different measured cross-sections. And you see that it doesn't look like that good. It's too high, and you have this double peak structure, and it's coming from some kind of interference here. In the next step, we also included this degree of freedom. The theta was still frozen, and this is the result now. This is the cross-section, and you see it dropped in magnitude, and the interference effect was smeared out. So the second dimension reduced the magnitude, and the smeared out the interference effect. At higher energies, above the threshold for this three-body channel, we think that higher excited states should be included. Okay, HF is next. Okay, here are quasi-diabatic, again, potentials of HF. The ion is the black one. You have Rydberg states converging to this ion. And the ground state of HF is not shown. And you have an ion pair state, that's the red one here, crossing the ion at very small distances. Then you have a bunch of other resonant states going like this. HF is different compared to H2 because of the large electron affinity. The ion pair limit is actually below the n = 2 limit. And that makes it different. In this study, we didn't include any spin orbit couplings. We started by studying the ion pair formation. Okay, we first did a direct, just including the direct mechanism. That means, if I go back to the potentials, you include the capture mechanism when you capture an electron into this ion pair state, and then you assume that you just follow it diabatically. Okay, so this is the measured cross-section from cryo-ring. This is the result, and you see it's too low in magnitude. So what we did then was we included the electronic couplings here. And then you assume then that you can capture into one of these other resonant states that have a more favorable curve crossing. And then these will couple to the bound Rydberg states. You will go to the bound Rydberg state that will be then pre-dissociated by the ion pair state. By doing that, this is the cross-section we got. And you see now, the magnitude now is much better. It increased the magnitude, so it's the right order of magnitude, and you get these pronounced structures in the cross-section. We could identify these as Feshbach resonances from the bound Rydberg states. And we also, as I mentioned, the spin-orbit splitting was not included. And if you just, we believe that this will kind of smear out these interferences. Next, we use these quasi-diabatic potentials to also study mutual neutralization. This is now the result. This is a total cross-section. Here we do one calculation with no outer-ionization, and then we also include outer-ionization. By just letting these states, when they cross the ion, we let them be complex and include the outer-ionization width there that we have computed. Okay, you see a cross-section that in principle it's 0 up to a threshold, and this is a threshold where the n equal 2 limit opens up if you neglect spin-orbit splitting and so on. And then you see this cross-section that has this series of peaks here. You see that when you include outer-ionization, the cross-section is reduced and the structures is smeared out and broader. This is the partial cross-section. So you say n equal 1, n equal 2, 3, and 4. We could also label the structures here with the angular momentum quantum number. Next, we are working on helium plus H minus. This is what we're doing right now. Okay, this system is kind of interesting also. Here I show you some potentials we have calculated. So helium H is nice because, again, it's a small system. You can do really good quantum chemistry on it. However, it's still a very complicated system. Here you see the potential curve of the ground state of helium H plus. You have now, remember, you have Rydberg states, an infinite number of Rydberg states converging up to this one. But they are not shown here. Then you have excited states of helium H plus here. And you have Rydberg states converging up to these. The ion pair state, you see it here. You see the avoided crossing here from the ion pair state. So all these states here are above the ground state of the ion. So they are electronic resonant states. Here we have done just a full configuration interaction calculation, and then we have extracted these states by looking at the configurations of the states. So then you can separate them out from the ionization continuum. When you do this calculation, and since they are electronic resonant states, I mean, you really have to do electron scattering calculations, and we have done that also. And the dots here are what we get from the electron scattering calculations, and the lines are what we get from the structure calculations. And the electron scattering calculations, we cannot afford to do the same big CI as we do in the structure calculations, but you see that still we get, I mean, they look quite close. So next what we are working on is to calculate the non-adiabatic couplings among these. And it's, the problem is that they are so highly excited, and yeah, then it can be quite difficult. But we will get it. And what we will do then is to do a strict diabatization of the states, including these non-adiabatic couplings. So that's the goal. We have, I mean, actually the first project I did was to study ion pair formation in helium H+. And then what we did was we used quasi-diabatic potentials where the couplings were obtained by semi-empirical formulas. And this was the result from that calculation. And as you can see, you just see, in this case, no interference effects or anything like that. However, this cross-section has not yet been measured. But it would be interesting to see what we get when we really do a strict diabatization and recalculate this one, as well as do mutual neutralization. Okay, so that's next. to calculate the non-adiabatic couplings, do a strict diabatization, and study mutual neutralization and this ion pair formation. And include auto-ionization in this study. So, summary. So I've shown you some examples of theoretical studies of ion pair formation and mutual neutralization. And the reactions are interesting because they probe the same molecular systems. They probe the same kind of dynamics. To describe these processes, we have to include non-adiabatic interactions. Some of these interactions are, they are among highly excited states, and some of them are at very large distances. I'm interested in quantum effects. So reactions where you see these kind of interferences or resonances formed. And this is not finished. This is what to do. What I think can be improved is, first of all, I mentioned this diabatization procedure, that in principle we have an infinite number of states interacting. And then it's not trivial how to do this. And when you go to polyatomic systems, then it's become much more complicated. Also, we haven't considered other types of couplings here. You have rotational couplings, spin-orbit couplings. We don't really know what's the effect of those. When going to larger systems, we could consider doing semi-classical studies, or, for example, mixed quantum classical molecular dynamics, including surface hopping techniques. Okay, some acknowledgements. So in my group, I have this Sifiso Nunkambule, that's just a new PhD student. And then I have to acknowledge my former PhD students, Mikael Stenrup, who did the studies on mutual neutralization in H++ H-. Johanna Brinner-Roos was working with the HF and H3, and my former postdoc at Ultimate Psi, and Professor Nils Elander. And I have a long ongoing collaboration with Professor Anne Orell from UC Davis. Thank you.
Thank you very much. So this talk is open for discussion. Questions?
Early on, when you looked at the H+, H- mutual neutralization, at low energies, I think you went down to 10 to the minus 3 eV, and the curve was just rising.
Yeah.
And do you have any idea of that dependence and whether that would continue to much lower energies?
Well, I suppose it's like the Wigner threshold law, that you have a 1 over E dependence
It
there.
should go like 1 over E?
Yeah.
Okay.
So in the same process, H+ and H- is giving you the dissociation. You left out the n equals 4.
Yeah.
That's maybe too complicated at the
But
moment.
yeah, it was
at that
because of
moment,
the
yeah.
quantum chemistry.
But nevertheless, the results are quite good. So how do I interpret this? This gives a cross-section that you left out, but that was also left out in the experiment.
What do you mean?
It's not seen in the experiment. Okay. So you don't include that?
But you could.
Don't include it.
No.
There is no signature of it. I will show results that show the end product. You see that there is no n equals.
Okay, that's an interesting issue because we did see in the bound region of the H+, H-, we did see decay to the n equals 4.
Yeah.
And so, as we learned from Frederick this morning, this continuity of oscillator strengths, of the channel, if you have this effect below the threshold, it should be above the threshold as well. Is that an issue?
I think the population of the n equal 4 proceeds via short-range couplings. What you see is not a
Yes. Yes, that could be, yes.
Yeah, the coupling are out.
Yeah.
It's very, very small if you look at the electronic coupling to the n equal 4.
That's an interesting conclusion, yeah.
Yeah, and we're not.
Very large.
Yeah, yeah.
Because when you cross on the way in, and you cross back on the way out, that doesn't happen.
Well, we'll have a chance to see that data, yeah. Yes? No, it'd be good.
So you have selected several processes, but can you look at associative ionization as well?
Yeah, I guess so. In principle, yes.
Yeah, in
Yeah,
principle
yes.
you have all the
Yes.
ingredients for
Yeah,
that.
I have, yeah.
Why I'm asking this is because for helium plus H minus, we did this associative ionization with hydrogen and deuterium. And that's the only system where we see a very strong isotope effect. in
Oh,
the
that
associative
would be
ionization.
interesting. Yeah, that's an interesting one.
Any other comments, questions? If not, let's thank us again.